So in this video, I'm going to show you how to solve differential equations using power series. This is the longest of all the processes that we've come across so far, and as far as solving differential equations. And so I figured it would be good to put in a video so you can pause at any time, take some good notes on this, and then we'll do some more problems in class tomorrow. So we're going to solve differential equations that look like the y double prime plus p of x times y prime plus q of x. So notice that these can be first order or they could be second order. This one is specifically second order. And then they're not constant coefficient. So these coefficients here, this p of x and q of x, those can actually be functions, and that's where this method becomes pretty useful. So what we're going to do is we're going to assume a solution looks like this guy. So this is a power series centered at 1. You might have to look back to Calc 2 notes to remember that. But a power series is a way that any function can be represented, and it's as a polynomial. So if you start plugging in n's, and I did that right down here, then when you plug in n equals 0, you get a naught. When you plug in n equals 1, you get a1x. When you plug in n equals 2, you get a2x squared, etc. So in other words, any function, any y, could be written out as this polynomial. So our goal in all of this and solving this is actually to find these a's. That's the goal. Once we have those a's, then we can say, yes, this is the solution. So we're going to do that how we've been doing that, which is basically guess, plug it in, and then check. So we make our guess of this y, we plug it into the differential equation. Now here are the derivatives for that power series. For any kind of a polynomial function like x squared, x cubed, etc., when you take the derivative, you take the number in top, so that n, and you bring it down in front, so there it is, n, a sub n, and then you subtract 1 from the exponent. So this is just using a power rule to find the derivative. Now because the derivative of a constant, the derivative of a naught is 0, it shifts where that sum starts. So the second derivative, same thing, it shifts because that first one is a constant, becomes 0. The n minus 1 comes down in front, and then another 1 is subtracted from the exponent. So you're going to take the second derivative, the first derivative, and y, plug it all into the differential equation, and then at that point you're going to get some x raised to different exponents. So you're going to shift all of those so that they are all just x to the n. The reason is we want to collect everything that's an x to the n. Then what we're going to have to do, because that will mess up the index of some of these sums, we want them all to be the same. So we're going to plug in so that what you end up doing is plugging in a couple numbers into that sum so that they all will actually start at the same index. Once you get it to that point, you can get a sum of all this stuff started at the same point and then factor out that x to the n. Now because this is all set equal to 0, we can set all that stuff equal to 0 and then solve for the biggest a sub whatever. So notice there's an a sub n, an a sub n, and a sub n. Those are going to get shifted. They're going to have different a sub n minus 1s, n minus 2s, etc., n plus 1s. Solve for the biggest one. And then start plugging in values for n. It's going to be dependent on where the sum starts. So if the sum starts at 0, you start plugging in 0. If the sum starts at 1, you start plugging in 1. And those are going to let you to solve for a naught, a1, a2, etc. So that was the whole goal. Then once we have those, we can plug those back into our solution. This is what we guessed originally. It's just expanded. And then once we have this, if we can recognize it as a known Taylor series, we can convert it back to an actual function. Alright, so there are all of the instructions. Let's go ahead and do an example. So in this example, we are going to solve a pretty easy differential equation. Let's just solve y prime plus 2y equal to 0. So remember that we're going to start off with the sum from n equals 0 to infinity of a sub n times x to the n. And we only have a first derivative on this one, so I'm going to find the first derivative so I can plug it in. I know it shifts the index, so it's going to start at 1 instead of 0. That's from that first part of it is a constant to become 0. The n comes down in front. A sub n is a constant, it stays there, x to the subtract 1 from that exponent. So now these get plugged into that differential equation. So this would be the sum from n equals 1 to infinity of n a sub n x to the n minus 1 plus 2 times that y, which was the sum, n equals 0 to infinity of a sub n x to the n. This is all equal to 0. Okay, so I just plugged into the differential equation. So now what I want to do is make this x to the n minus 1 and x to the n. I already have one here, but I want this one to be x to the n. So what I'm going to do is for every n, I want to plug in n plus 1. So here on the sum, if I plug in n plus 1 and I set it equal to 1, then subtract 1 and I get 0. So now what this does is it now shifts this so it's back at 0. There's an n, I'm going to plug in n plus 1. There's an a sub, there's another n, I'm going to plug in n plus 1. And then into the x, the whole reason we chose this n plus 1 is because n plus 1 minus 1 is n. And we get x to the n. Now this other sum we don't need to do anything with because it is already has that x to the n in it. So I'm just going to write that guy down again. Alright, now the next step said to make these, make the index the same. Now, these indexes are already the same, so we don't actually have to do that step. The shifting already did it for us, so that step is done. So now what we want to do is collect this into one big sum. So here's an n plus 1, an a sub n plus 1. And the other thing I want to do is factor out that x to the n. So in this first term, the n plus 1 and the a plus 1 is left over when I factor out x to the n, and then the next one, the 2a sub n, is left if I factor out an x to the n. So x now can't be 0, because if x is 0, then our whole solution is 0, and we're back to that, what I call the dumb solution. I mean, it always is a solution. It's there, it just doesn't really get us anywhere. So to get us somewhere, let's look at this other stuff and set it equal to 0. So I'm going to take n plus 1, a sub n plus 1 plus 2 a sub n. I'm going to set all that equal to 0. And I'm going to solve for the largest a sub, which is a sub n plus 1. That's bigger than n. So I'm going to solve for that one. So I'd have to subtract over 2a sub n, and I'd have to divide by n plus 1. Okay, so I'm going to need to remember this because I'm going to switch slides here, and we're going to need this. It's called the recurrence relation. Alright, so that was a sub n plus 1 was equal to negative 2 a sub n all over n plus 1. Okay, that's where we left off. So now I want to try to find my a0, a1, a2, etc. And so to do this, I'm going to start plugging in n's into this equation. The sum started at 0, so I'm going to start at 0. So starting at 0, that's going to give me a sub 1. A sub 1 is going to equal negative 2 a sub 0 divided by n plus 1. I'm going to plug in n equals 1. This is going to give me a sub 2. Now when I plug in n equals 1 up here to the recurrence relation at the top, it's going to give me negative 2 a sub 1 divided by n plus 1. Oh, sorry. I need to back up there, don't I? I forgot to plug in my n's into those. Okay, so I got to back up to 0. When I plug in 0 into that first one, I get 1 in the denominator. When I plug in, and I'm plugging in 1 into this next one, then I get 2 in the denominator. There we go. So now notice that I know a sub 1 from the step up above. So a sub 1 is equal to negative 2 a naught divided by 1. I'm going to plug that into there. So then I get this negative 2 times the negative 2 from the one up above. So that is a 2 squared a naught divided by 2 times 1. You'll see I'm writing that like that for a very specific reason in a minute. Alright, now let's plug in n equals 2. That's going to give us an a3. a3 is going to be negative 2a2 divided by 3. Now I know a2 from the step up above, so I'm going to plug that in. So that's a negative 2 times this 2 squared, that's a negative 2 cubed, a naught, divided by, now 3 times 2 times 1. I'm going to do one more. Really, I just keep going on this until I can see a definite pattern. So a4 is going to be negative 2, a3 divided by 4. That's plugging in n equals 3 into this above equation. And so that is now negative 2 times negative 2 cubed is positive 2 to the 4th, a naught, divided by 4 times 3 times 2 times 1. Alright, now I'm going to take all of these and plug it into the expanded sum. We started off with the sum from n equals, can I write that in here? The sum from n equals 0 to infinity of a sub n x to the n. That's what we started off with. So I'm going to expand that. I plug in 0, I get a naught. I plug in 1, and I get a1x. I plug in 2, I get a2x squared. I plug in 3, I get a3x cubed. I plug in 4, I get a4x to the 4th. Okay, I think that's enough. So now I'm going to take all these a's that I just found, I'm going to plug them into this equation. Now a naught, everything else is in terms of it, so I'm going to leave it, a naught. a1 was negative, I can take away that positive sign there, negative 2 a naught, and that's times x. a2 is 2 squared a naught divided by 2 times 1, and that's times x squared. a3 is minus 2 cubed a naught divided by 3 times 2 times 1. That one's times x cubed. And a4 was 2 to the 4th a naught. That's times x to the 4th, and then all divided by 4 times 3 times 2 times 1. And this would continue. And we just need enough of these to really see the pattern. I think on this one I might have been able to really just stop right here. I can see that there's a pattern, plus, minus, and a 2 raised to a 0, a 2 raised to a 1, a 2 raised to a 2, a 2 raised to a 3, a 0 factorial in the denominator, 1 factorial, 2 factorial, 3 factorial. By the way, fact, if you don't remember it, 0 factorial is in fact 1, and if you're curious about the proof of that, I'll show it to you at some point. Alright, so now what I want to do, this is a solution. We can write a solution like this, but it's much nicer if we can put it back into a single function. Now, back in Calc 2, you saw that the Maclaurin series for e to the x was the sum from n equals 0 to infinity of x to the n divided by n factorial. Now the reason that I'm looking at this one is because we have an n factorial in that denominator. We've got a 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc. So I want to try to write this entire big thing that's all written out here. I want to try to squish it into a sum. Now all of these terms have an a naught. I'm going to factor that out. And then I want to try to squish everything else with the a naughts into a sum. Starting at 0, I want it to start at 0 because this e to the x1 starts at 0. So one of the things that I notice, and I do this piece by piece, so I'm noticing that it goes from plus, minus, plus, minus, plus, minus, etc. So that would be a -1 to the n, would make that sign oscillate. All of these in the numerator have a 2 raised to an n. They also have an x raised to that same number. And then the denominator has an n factorial. And so I just looked at every single little piece. I looked at the plus minus, I looked at the 2's, I looked at the x's, and then I looked at the n factorials all separately. This can be written as that a naught staying out in front, the sum from 0 to infinity of all of these things in the numerator are all raised to an n. So I can rewrite this as -2x all to the n power. It's divided by n factorial. And if you now look, this looks almost exactly like this, except that the only difference in it is this x right here. So that x goes into the numerator here, and so because here it is a -2x, our solution has that a naught, and then we're going to get an e to the -2x, and e to whatever was in blue in there, because that's what was raised to the n. And there is our power series solution. All right, 2 more things of note before you go and try some of these on your own. If you have a second order, for second order differential equations, remember that we normally get 2 solutions. And so because of this, when you write out your end solution, you get stuff with a0s and stuff with a1s. And so what you want to do when you get to the end is factor out the a0s and then factor out the a1s, and then turn these and find these in terms of their power series solution. So whatever is multiplied in here, this is what you want to simplify and get down to a single function. All right, so that's kind of one hint. And then another one is that sometimes on these we don't know known Taylor series. So sometimes you have to just leave it in the expanded form. And this is because there is no known Taylor series to be able to kind of shrink back down the sum. Actually, sometimes the sum even can't be, you can't find a pattern to it to actually shrink it back down. And then sometimes even once you can shrink it back down, there's no known Taylor series for that. Very rare, but it can happen.